Hello, and welcome to the molar volume of a gas notes. Molar volume of a gas will allow us to do conversions whenever we have a gas between liters and moles. 1 mole of any gas at what we call standard temperature and pressure, which is a set of conditions that are actually listed on table A of your reference table. 1 mole of any gas under these conditions will occupy actually the same volume of space, 22.4 liters. When we say this number, it's nice to kind of get a handle on this. If you picture a men's basketball, this is actually a little bit bigger than that. So 22.4 liters of gas is actually a decent amount of space. So let's talk about this for a minute. If I have these 3 separate containers here that I keep at these same conditions in a container that's the same size, and I have the same amount in each one of them. So in each of these containers, imagine I had a mole of the gas in question, and I kept them at standard temperature and pressure, which is 1 atmosphere of pressure and 0 degrees Celsius, in a container that has a size of 22.4 liters. What I actually find out that's kind of interesting is that the masses of these gases don't actually matter. So the mass of this argon gas, if we had 1 mole of it, would be 39.948 grams. Whereas the mass of my sample of nitrogen gas that I have over here would have a mass of 28.0, okay, I'm going to round, lazy, sorry. But we have a mass difference here between 38 and 28, or 39 and 28. And then our last sample over here with our hydrogen gas would have a mass of about 2.01 grams, if I kind of round that a little bit. So what this actually tells us is something very interesting, that if I have the same volume, temperature, and pressure, I will actually have the same number of molecules, even though the mass is different. So even though the mass of the particles are different, they're occupying the same amount of space under this set of conditions. So there's a little song that goes along with this. We'll sing this in class that tells us Avogadro's hypothesis, which is that equal volumes of gases, the same temperature and pressure, contain the same number of molecules. Again, there's a little video for this. We will take some time to listen and sing that in class. It's very helpful in trying to remember this. So I'm telling you that very different grams of 3 substances held at the same conditions are occupying the same amount of space. This is weird. Yes, it seems crazy. What if I said to you, I have 45 basketballs and 45 golf balls, and they're taking up the same amount of space? You'd say, you're crazy. So why does it work? If you think about why this is, there's something very important about what we know about gases. When you think about gases and how their particles are laid out, their particles are very spread apart. And that's very important to this. If we visualize 14 hydrogens versus 14 argons, you'll notice they could occupy the same amount of space. There just happens to be a little less blank space in between them. So that total volume that they occupy can actually be equal, even though the individual particles are smaller. Because gases are so spread out, this is actually what occurs. We just happen to have a little bit less white space in the middle. So it's kind of nice because it makes for some easy calculations for us. We know that if we have a gas at STP and we have 22.4 liters of it, that's 1 mole. If we had 44.8 liters, that'd be 2 moles. So we can do some nice, easy calculations here. Our possible conversion factors that we're going to have are either going to be 22.4 liters in 1 mole, or 1 mole is 22.4 liters. Now, these are, condition dependent, but in this particular course, we just stick to STP. So in the future, you might have to do calculations where that's not the case, but for our purposes, we stick with STP. So we have a sample of gas at STP, which means that relationship will be useful to us, occupying 12.5 liters. How many moles are in this sample? So we're going to go right down here to do our little dimensional analysis. and we have 12.5 liters. I want to get this into moles. I want my ending amount to be in moles, so I need liters to be on the bottom to cancel. So I'm choosing this one right here. That puts my 22.4 liters on the bottom. And what I'm actually doing mathematically is dividing 12.5 divided by 22.4, which will give me 0.558 moles. And that makes sense. So that's about half of 22.4, a little bit more. So we have a little bit more than half a mole. If we look at this relationship the other way around, if we're at STP, 1 mole of the gas is going to equal or occupy 22.4 liters. If we had half a mole, it would be half of this, so it would be 11.2 liters. So if we wanted to solve how many liters will 2.5 moles of oxygen gas occupy, sorry, I should have said at STP, we'll assume that we're at STP. I'm going to need moles on the bottom here, so 1 mole equals 22.4 liters. Your moles are going to cancel, and you can go ahead and multiply, which will give you 56 liters. So we're limited to 2 sig figs here. Now, we can also include grams in this. So if we need to include grams, we would start with our 4 liters of oxygen gas. In order to go in grams, I'm going to need a pit stop at moles. So I need to get rid of my liters. So I'm going to put my 22.4 liters on the bottom and 1 mole on top. I don't need to worry about directly relating liters straight to grams, because I can stop off at moles. And then I've got my GFM for O2 I already calculated is almost 32 grams per mole. So I've got 1 mole on the bottom to allow that to cancel. 31.9988 grams on top. Moles go away. I'm going to multiply across the top, divide by the bottom to give you 5.7 grams. We're limited to 2 sig figs from the 4.0 liters. So if we started at grams, we could say, okay, oops, I don't like to write in red. We started with 66 grams of carbon dioxide. First thing that we're going to do now is we got to get rid of grams and go into moles, which will allow us to go into liters. So we're going to put our 44.0098 grams on the bottom, and we're going to put our 1 mole on top. Grams are going to cancel. Now I can take my moles into liters by putting 1 mole on the bottom and 22.4 liters on top. And again, multiply across the top, divide by the bottom. We can keep 3 sig figs here, and we've got 33.6 liters. Here are a couple problems to try. Pause your video for a minute, and I'll expose the answers in just a moment. So here you go, your first one, you get 39.8 grams. You have to get rid of liters in your first term to go into moles, and then you put moles in the bottom in the second one to get rid of moles and turn that into grams. And the second one, you're starting with grams. Get grams to cancel, you go into moles, and then from there you go into liters. So I do want to quickly mention these tend to look a little bit different on the reagents. The reagents just goes back to that statement, which we'll say in class tomorrow, which is that equal volumes of gases at the same temperature and pressure contain the same number of molecules. So we're assuming all these are STP, which is the same temperature and pressure. So we want to know which will have the same number of molecules as 3 liters. And the answer is just whatever is 3 liters. In the next one, we see temperature, pressure, and volume for several samples. We want to know which is going to contain the same number of molecules as sample A. So we have to have the same condition. So you need 273, so it can't be those 2. You need the same pressure, so it can't be those 3. And you'd also need the same volumes. That eliminates those. So it has to be sample 2.